All right, well, I had a little glitch. My camera stopped recording at one point. I wasn't very far past, I didn't talk for long without being recorded. And I was able to, I hadn't erased the board much since then, so I was able to basically restore the board to, I think, where we were. You may see a little weird spot at the end of one file and the start of another, which of course you won't be able to tell. I'm going to just check this thing every now and then to make sure it's still recording. It seems like it is. I wave my hand in front of it, it is seeing that. So I'm going to assume that things are working at the moment. Let's continue on with this problem. Might be a good time to just say what's happening is that you've got this coordinate system, so x is into the board, y is over there, x is into the board, y is over there, z is down. We've got a constant B field, a constant and uniform B fields and E fields, and we shoot Q into this region of space where B and E exist with some velocity in some direction. Okay? We've worked through all of that. We're in the midst of an example where we say, okay, I'm going to start with my particle here, like this yellow lid on the cap, and I'm going to say that's the origin, and I'm going to give it a starting velocity in the y direction, so I'm going to give this thing a thunk that way. We're in the midst of determining our four constants, and we're down to one. We've done z of 0, y of 0, z dot of 0. Now let's do y dot of 0. Y dot of 0, according to this, is E over B minus C2. And y dot of 0 is our starting speed. And that means that C2 has to be E over B minus V0. So let's fix that everywhere. C over 2 is E over B minus V0. C2 is E over B minus V0. C2 is E over B minus V0. C2 is E over B minus V0. And finally, C2 is E over B minus V0. And so we've gotten rid of all four, C1, C2, C3, and C4. Let's write down our summary equations over here so they're a little easier to look at. Y as a function of time is E over B times T minus the quantity E over B minus V0 instead of omega T. Y component of the velocity as a function of time is E over B minus, I sure seem like I'm missing an omega someplace. E over B minus V0 cosine omega T, which I think is going to need another omega someplace, I think. Hang on a second here. Well, I think that's right. The units are correct there. Yeah, the units are correct there, I believe. Z of t is E over B minus V0 as a factor, 1 over omega as a factor, 1 minus cosine omega t, and z dot as a function of time is E over B minus V0. So I have omega t. Let me check those with my lecture notes. See if this makes good sense. Why? Somewhere I lost an omega here. don't know when that happened. It probably happened as I restored my conditions from the positive video. I had to rebuild the board. It looks like I lost a little bit of something. So there's a 1 over omega right there, which makes sense because units of t and units of 1 over omega are the same. Well, can you describe that motion? When we pick it apart, let's look at individual. Z is the up and down motion. Well, what you see here is you see oscillatory motion. This will vary anywhere from the number 2 to the number 0. And so Z, here's an amplitude because E, B, V naught, omega are all constants. So Z varies between the Z equals 0 location and the Z equals 2 location. So the Z motion, which is, it's down is positive. So the Z motion is going to start, it's going to go down, up, down, up, down, up. That's what the Z motion will do. What will the Y motion do? Well, it will also oscillate back and forth in the Y direction, but in addition, Y just keeps growing due to this. So the Y motion of our little object would be something like this, back and forth. If that's a slow motion, then it might be like this. If it's a fast motion, then it might be overlapping. So we've got this back and forth combined with an up and down, back and forth, and I'm not clever enough to move my hand that way. But there's a motion, if V0 is a very small number, then it doesn't affect this much. If V0 is a very large number, see it's going to change the sign of that term, which is going to change a phase. So we've got from in phase to out of phase, or something like that, and how these all work out. Okay? Very good. Now, let's do even an application of this example. In my example 1. Let's look at the device here. That is what we have on the board, actually. I'm going to put in a pair of capacitor plates. Let's move those over just a little bit. A pair of capacitor plates like this. Positive high, negative low, that's going to make an E field that points down, which is the Z direction. So we'll have an E field points down. So that E field is red, I guess. There's our electric field. And then we're going to think about having a big magnet whose positive face is out here, whose negative pole is behind the board. E field lines go from, I'm sorry, not positive or negative, it's a magnet. Whose north face is out here, whose south face is behind the board. E field lines go from north to south, so we've got an E field that's pointing in the X direction, just like that says. So here's my E field, and I'll put that in uniformly also. So there's my cross E and E fields that I'm going to pretend at least are uniform. It would be hard to make them shut off at specific places, particularly the magnetic field, but that's okay. And this would be three-dimensional, of course. It would extend out this way into space a little bit, back into the board a little bit, and so on. And now I'm going to take and shoot some particles in here. With a range of V0s. So we'll shoot some particles in slow, some particles in fast. Okay? A whole range of V0s, of particles, shooting into that region. There's going to be an electric force, which is going to be which way? Assuming they're positively charged particles, there's going to be an electric force down. It's going to tend to pull those particles down, just like I throw something sideways and a uniform gravity field is down, pulls the particle down. Okay. There's also going to be a magnetic field, a magnetic force. that. V cross B, it's an upward force, so there's going to be an upward force due to the magnetic field. Okay? So let's say we shoot in a particle very, very slowly. The upward force is small. Relatively speaking. The downward force is not changing, so we've got a very small upward force, so the particle's going to tend to curve down. Let me use another color. Let's take blue for my velocities. I've been watching too many Khan Academy videos about color. Oh no, I used blue already for the magnetic field. Let's use green. Can you tell my attention is starting to drift here? Green, 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 markers. So here goes a particle, and it's kind of slow. I do that. It's even slower. And do that. Now let's shoot at a particle. It's pretty fast. That means there's going to be a big force trying to push it that way. Still be a downward force, but let's make it really fast. It's going to tend to curve up. Shoot it really fast. Why do that? Because the upward part depends on velocity. So if V is relatively large, we're going to get something like that. Well, what if we, like Goldilocks and the Three Bears, choose just right? This is Papa Bear. My particles are going too fast and they grew up. This is Mama Bear. My particles are coming down because they're going too slow. What would Baby Bear do? What if I go just right? What does just right mean? It means that there's no general tendency to drift up or down. It means those two forces have to be the same. It means that V has to be E over B. Just right means the speed of all these different particles coming in has to be E over B. The particles that have just that right speed, they go through undeflected. And that's why this thing is called a velocity selector. It picks out the velocity E over B. What happens to our equations if E over B is equal to V0? Then Z is exactly 0. And that means Z dot is exactly 0. And that means that Y dot is a constant. And it means that Y V0t, distance equals rate times time. Just right speeds go straight through. I mentioned before, I think, that my daughter works as a medical physicist, which means she uses radiation, she uses charged particles to treat cancer patients. And the doctor will prescribe a certain energy. I'm going to check my video, make sure it's still running. Looks like it is. Yes. The doctor will prescribe a certain energy, which means a certain speed of the charged particles that are going to strike that tumor. How does my daughter's machine pick the right speed? By adjusting E and B fields inside the machine. A whole range of V0s is thrown into the machine, but the only ones that come out in the right direction, and you can make that right direction happen by building some walls. How about a little wall right there, a wall right there, a wall here, a wall here. Particles go in, but the only ones that come out are the ones that are moving just right. And you know exactly what their speed is. So you know exactly what their energy is. Let's take this velocity selector and use it as the front end into a mass spectrometer. Which again has a big B field in here, and we'll call it B prime. So here comes particles of speed V0, a known speed. They hit this region and they curve around like this. These are ions. They're charged. So we know what the charge is, let's assume. We know what the radius is, we can measure that with this device. We know what B prime is, the magnetic field in our mass spec. We know what V0 is, which is UV, and from that we can determine the mass of the particle. I have to dig back through some of the formulas that I've erased, but you can come up with what that is for our mass spectrometer. All right, almost done. One more sample to do. So we're going to go back. We're still going to use the same arrangement. We have the crossed E and B fields that are uniform. Same directions that we've said. I need to restore these equations to their original values. So I'm going to have to copy those back down from the lecture notes. Speaking of the lecture notes, I will post them probably today or tomorrow, so you have all of the Chapter 4 lecture notes with you. You can use those as you work on Chapter 4 homework, which probably won't get done today, but maybe tomorrow. Plus, you're not ready for homework anyway. You're working on an exam, I hope. If you're having any difficulties with that exam, let me know. We'll see if I can help, or if Prof. Kears can help. That was right. Y dot was equal to B plus C1 sine omega T minus C2 cosine omega T. Z was C1 over omega sine omega T minus C2 over omega cosine omega T plus C3 and Z dot C1 cos omega T plus C2 sine omega T. Make sure those are right. And where did those equations come from anyway? They came from solutions of the differential equations that arise from the Lorentz force when you have this specific E and B. So if E and B are something different, well then you get totally different equations of motion here. You get different trajectories. I'm going to keep wandering back here from time to time. It gives you a chance to write what's on the board, but I'm just a little nervous about this thing stopping on me like it did last time. Okay, well, we do the same sort of an idea again, in that if I specify starting positions and starting speeds, you should be able to determine the trajectory of the motion. Let's uncheck all of these now. We have to start this process over again. We're going to now start, you know how we started with our particle at a certain location in space here, my little yellow cap on the water bottle. For this example, let's start with, at the origin, y of 0 equals 0, z of 0 equals 0, and let's let it be at rest. So it's this, if this is my charged particle, I have it here at the origin, and I just let go. What's going to happen to it? Well, obviously it's going to start to go down, because assuming it's positively charged, the E field is going to pull it down. But once it starts to go down, it's got a speed. That speed is perpendicular, the velocity is perpendicular to the magnetic field, which means there'll be a magnetic force, and start to do it in some complicated fashion. All right, let's use our initial conditions. Let's start out with z of 0 equals 0. But z of 0 is minus c2 over omega plus c3, which tells me that c3 equals c2 over omega. Y of 0 equals 0. Plug in t equals 0, plug in t equals 0, minus c1 over omega, plug in t equals 0. This tells me c4 equals c1 over omega. Let's go ahead and make those changes. Every place there's a c3, we can change it to say c2 over omega. Every place there's a c4, we can change it to say c1 over omega. And I've used this equation, and I've used that equation. Now let's say z dot of 0 is equal to 0. Well, z dot of 0 is just c1. So c1 is 0, so let's get rid of everything that says c1. And y dot of 0 is equal to 0, which is e over b minus c2. 0, which tells me that c2 is e over b. So let's change all the c2's to e over b's. We probably could have just taken our answer from the last problem and said, oh, let v0 be 0. And come up with these equations, perhaps easier. Excuse me. But I think it's good for you to go through the exercise. Good for me to go through the exercise. There's everything. So let's combine all this into final equations. Y equals e over b times t minus e over b omega sine omega t, which I write as y equals e over b omega times omega t minus sine omega t. And z is equal to, factor out an e over b omega again, 1 minus cosine omega t. And I won't write down z dot. Well, you see kind of the same idea. There's still some oscillatory motion in each case. Oscillations because B fields make things go in circles. And if you combine circles with other motion, you get things like helixes, so forth. Let's see what I'm going to say about this. Turns out I've got an Excel demo for this. I'm not set up to run things on the screen. I'll have it posted on Blackboard, most likely. However, you've done this problem before. I'll show you that in a minute. But in fact, I'll show you that right now. An example. (1.10.3). We worked through that in class in great detail, and I think that was one of your first mathematical assignments, was I asked you to do things like plot the motion and the speed, acceleration, and things like that. But here is part of that problem. We had that the x coordinate was b times sine omega t plus omega t, and the y coordinate was b times cos omega t plus 1. You see how similar that looks here? The only thing difference is a phase shift. Because you make sine of omega t into negative sine of omega t just by adding pi to it. So you call this sine of omega t plus pi. Same thing with cosine. This was our cycloid, which is the motion of, let's say you put a blinking light on the rim of a bicycle wheel and then roll the bicycle wheel down the street. The motion of that blinking light in the x and y directions, or in our case, in the y and z directions, would be cycloid motion. So we get the cycloid again in a totally different way. Instead of a wheel rolling on a surface, we did that problem with relative velocity of the center relative to the edges, or the edges relative to the center, so forth. We get the same kind of motion for this. I think that's really interesting. Let me do a little algebra trick with our solution here. But one of the things maybe to get from a course like this, just in your toolbox, in your bag of tricks, in your way of thinking about engineering and physics, is, oh, I see sines and cosines. Is there anything special about sines and cosines? Yeah, a lot of stuff special about sines and cosines. They're just a phase shift away from each other. You can combine them to get tangent. You can square them and add them together to get 1. There's lots of algebra tricks to do with that. So, I'm going to do an algebra trick. Well, first of all, what units does E over B omega have to have? Well, this is unitless, that's unitless, this is Z. E over B omega has to be some sort of a length or a distance. Since I know the answer, I'm going to call it capital R, which makes you think movies. So Y equals R omega t minus R sine omega t. Z equals R minus R cosine omega t. Let's isolate the sine and the cosine. R sine omega t equals R omega t minus Y. R cosine omega t equals R minus Z. Square them, add them together. I'll get R squared sine squared omega t, R squared cosine squared omega t. I thought I heard this thing make a funny noise. Nope, so it seems to be fine. So square them, add them together. We get R squared equals this quantity squared. Do you believe that this is the same thing? Does it matter whether I have y minus r omega t or r omega t minus y? If I'm going to square it, and this is the equation of a circle. Radius r and its center is at y equals r omega t. Oh. So the center moves. Which way? In the y direction. At speed r omega, which is a velocity. The center moves to the right. So this thing is making a circle like this. Z is up and down. Y is back and forth, but the y moves off to the left. And that's exactly what you did in example 1.10. Again, this is called like a drift velocity. The y component, y drifts at a speed of r omega. The center of that circle is drifting to the right. And what determined omega? And what determined r? The E field, the B field, and omega, which what was omega? Well, that's where that went. I have to look at it to see what omega was, but it was related again to the parameters of problem. Okay, well, that's the end of the actual lecture portion. Let's talk about a homework problem I'm going to assign you from this. So let me just sketch out what this homework problem would be. Very sketchy. If I wanted to write on the board for another 5 minutes, I would restore those 4 equations. And then we're going to do, if you know the starting position and the starting velocity, figure out the 4 C's and figure out the trajectory. Well, here's what I want the starting velocity to be. So again, this will be on the homework assignment. You don't have to take notes on this and know exactly what it is because it'll all be written down. But given those 4 equations, which hopefully you've written down a couple of times in the lecture notes, we're going to say we're going to let the starting velocity be we'll parameterize it in terms of something familiar. E over B is a velocity. And then we'll say it's got some motion in the y direction and some motion. It's not y hat though. How do we spell it in this class? We spell it j hat. Some motion in the z direction. So alpha and beta are parameters to be adjusted. For instance, if you said alpha equals beta equals 0, you should get our case 2, which was the cycloid. If you said alpha equals 1 and beta equals 0, you should get the velocity selector. And as you adjust alpha and beta, you'll get different kind of combinations of those 2 motions. Some that will be cycloid, some that won't be cycloid, but look sort of like a cycloid, things like that. So you're going to solve the differential equations. Oh, and we'll let the initial position be 0. So so y of 0 is 0, z of 0 is 0, y dot of 0 is e over b alpha, z dot of 0 is e over b beta. Solve differential equations using initial conditions. Find C1, C2, C3, C4, and then I want you to plot the trajectory. In Mathematica. Parametric plot should do it. But I'm going to have you have alpha and beta be parameters that you can adjust with the manipulate command, so that as you tweak alpha and beta, you'll see your trajectories evolve based on how you chose those 2 parameters. For instance, what happens if this parameter is twice that one? What kind of motion